Hey everyone, and welcome back. Today we are going to pull back the curtain on one of the most powerful tools in machine learning, k-means clustering. We're going to see how this incredible algorithm can take what looks like a total mess of data and magically find the hidden groups and patterns hiding inside.
So let's just dive right in. Picture this. Someone hands you a massive digital file, maybe thousands or even millions of rows of data. But here's the catch. There are no labels, no categories, nothing. It's just a sea of raw numbers. Where do you even start? What secrets could be buried in there? Well, this exact problem is what leads us into a really fascinating part of AI. The key to unlocking all of those secrets is something called unsupervised learning. It's like teaching a machine to be a detective. You let it loose on the data, and its job is to find clues, connections, and patterns all on its own, without anyone telling it what to look for.
Yeah, at its heart, unsupervised learning is all about pure discovery. You're not giving the algorithm a cheat sheet with the answers. Instead, you're handing it a magnifying glass and basically saying, go explore. Tell me what you find. It's this amazing, unguided journey into the data.
And, one of the most common tools in this whole detective kit is called clustering. And it's exactly what it sounds like. It's the process of taking that chaotic jumble of information and starting to bring some order to it by grouping similar things together.
Which brings us to the star of our show today, k-means clustering. Honestly, you can think of it as a master sorter. It's an algorithm that is just exceptionally good at taking a huge, unlabeled pile of data and elegantly sorting it into these distinct, really meaningful groups.
The name itself actually gives you some big clues. The algorithm partitions, which is just a fancy word for divides, your data into a specific number of groups. We call that number K. And these groups, we call them clusters. The main goal is super simple. Make sure everything inside one cluster is as similar as possible to everything else in that same cluster. And here's where you come in. This is so important. The K in k-means isn't some magic number the computer just guesses. Nope, it's a number of clusters you, the human, tell it to find. Do you think there are 2 groups in your data? Or maybe 3? Or 10? You have to set K. It's really a partnership between your intuition and the machine's power.
So how does this whole thing actually work? How does the algorithm think? Well, it's not a one-and-done kind of deal. It's what we call an iterative process, which just means it tries and refines and tries again, getting a little bit smarter with each pass until it settles on the best possible groupings.
Okay, the whole process is kind of like a dance. It follows 4 simple steps. First, it randomly drops K starting points, called centroids, onto the data. Then, step 2, it looks at every single data point and assigns it to whichever centroid is closest. Step 3, it finds the new middle point of all the members of a cluster and moves the centroid there. And then it just repeats steps 2 and 3, assign, move, over and over until things stop changing and the clusters are stable.
But hang on a second. That second step is everything, right? Assigning points to the closest centroid. But what does closest even mean to a computer that just thinks in ones and zeros? It's an abstract idea.
Well, the answer for any kind of numerical data is something you probably remember from high school math class, Euclidean distance. It's literally just the straight line distance between 2 points, A to B. That's it. This super simple calculation is how k-means turns the fuzzy concept of similarity into a hard number it can work with.
And check out this table. It shows it perfectly. For each data point, the algorithm just calculates the Euclidean distance to a centroid. And as you can see, that point in row 1 has the smallest distance, right? Only 4.123. So boom, the algorithm decides it's the closest and assigns it to that centroid's cluster. Simple as that. So that's the logic. Calculate, assign, and repeat. It's elegant. But can you imagine doing that for millions of data points by hand? No way. Of course, data scientists don't do this with a calculator. They use really powerful programming libraries to do all the heavy lifting. And one of the absolute most popular for this in Python is a library called Scikit-learn, or just sklearn for short. The workflow in sklearn is beautiful. It's this clear 4-step pattern. First, you import the k-means tool from the library. Second, you instantiate it, which basically means you create your own custom version of the model. Third, you fit that model to your data. That's when the magic happens and the clustering actually gets done. And finally, once it's trained, you can use it to predict which group any new piece of data should belong to.
Now, that second step, instantiate, can sound kind of scary and technical, but I love this analogy from the source material. It makes it so easy to understand.
It says instantiating a model is like ordering a car. You don't just buy a car, you order a specific one with the options you want. The color, the engine, the number of doors. It's your own personal version. So when a data scientist is ordering their car, the most important option they have to choose is that N clusters parameter. This right here is the moment they set the value of K and tell the algorithm exactly how many groups to go looking for.
Okay, so this is all really cool from a tech perspective, but so what? What's the payoff? Why does finding these hidden groups actually matter out there in the real world? Well, the applications they're everywhere, and they're incredibly powerful.
I mean, seriously, you see this stuff everywhere. It's used to spot weird data points or outliers that don't seem to fit in any group. In marketing, it's the secret sauce behind customer segmentation, creating tailored ads for different groups of people. It can automatically sort news articles by topic or even help researchers find hidden patterns in things like student admissions data. The possibilities are just endless.
And that really brings us to the final thought here. The true power of k-means is its ability to create structure and find meaning where before there was just noise. So that leaves me with a question for you. If you could use this tool on any dataset in the world, what hidden groups, what secret patterns would you want to find?